Good afternoon, students. So, in this lecture we will continue with entropy maximization, and I will show a specific case of a dice that is biased. The probability distribution comes out to be Maxwell-Boltzmann type, or it becomes non-uniform. Okay. So, let us continue the discussion on entropy maximization. Or you may wish to call it as a maximum entropy principle. Okay. Now, we saw earlier that if you take a dice and say that its faces are all unbiased, which means there are 6 faces and the probability of each face, if you rule it n times, then it is expected that 1/6 of the n would be the probability, 1/6 of the n would be the number of occurrence of any ith phase. So, the probability of any phase comes out to be 1/6, where I is one of the 6 outcomes. Okay. Now, this was definitely the case when we discussed that the only constraint is the normalization of the probability. So, when the only requirement is that the probabilities are well behaved, then you get a probability distribution that is unbiased. So, I will call this as this result that we obtained in the last class as an unbiased probability distribution. Okay, so, this will be called as unbiased. All faces have equal probabilities. Now, today we will see an important result which is established in the context of biased probabilities. So, this will be the case of a dice where some faces have a higher probability of occurrence compared to the other. Now, what do I mean by this? It means that I have now 3 conditions. Okay. So, I am going to consider the case of non-uniform or biased PDS or probability distributions. Okay. Now, this simply means that I have my function of various probabilities as the entropy over NKB, which is given as minus summation I going from 1 to t. I am taking a t phase die again, pi ln pi as before, and my constraint so I will take constraints. Now, instead of one constraint I will take 2 constraints. So, the first constraint is my function g, again a function of all these probabilities P1, P2 all the way up to P of t as conservation of the norm. Okay. So, sum of all probabilities is 1. So, this is one constraint, and I have another constraint now. I call it as a function h, which is a function of all these probabilities, as the average outcome is fixed to some epsilon. So, the average would mean I call the outcome of each phase as epsilon I with the weight pi, and I is summed over all t possible outcomes, and this is basically nothing but epsilon. Okay. So, what this basically means that I have taken I have said that the die is biased in the sense that the average outcome is epsilon. So, this is like saying the average value of epsilon is fixed, which is nothing but I will call it as, I can simply write it as okay. So, definitely my second constraint is h. I have two constraints, and I want to maximize my function, which is entropy. So, my function is f, which is nothing but entropy per nkb, and I need to maximize my function which is entropy subject to the constraints, okay, keeping g and h intact. So, under these constraints I want to maximize the entropy, and you shall be surprised to see the outcome. So, our usual prescription as discussed in the last lecture, you can consult the last lecture if where we have derived the where we have discussed the concept of function optimization using Lagrange multipliers. So, you can consult that lecture. I am going to just use that concept here and say that I am going to define my Lagrangian L as a function f minus lambda times g minus my second Lagrange multiplier beta times h. So, this way, as I have said, if you have more constraints, for each constraint you will have a new Lagrange multiplier in the problem. Okay. So, a new multiplier, Lagrange multiplier for each constraint. Each physical constraint. Okay. This is the standard technique of a function maximization. Okay. So, let us put the values of our function. So, f as we know is nothing but minus summation over all i's going from 1 to t pi ln pi, okay, minus lambda times g, which is nothing but summation over all pi's minus 1, which is nothing but the conservation of norm, and the second Lagrange multiplier multiplied to the fixed value of the expectation of the outcomes. So, that is nothing but summation I going from 1 to t epsilon I, the outcome of each phase, times the probability of each phase minus the average value itself. Okay. So, these are the two constraints, and I know that the solution of optimization is a probability p of j, and if p j is the solution, that is p j optimizes the entropy or the function f, then del L by del p j should be 0, okay, should be 0. So, let us compute del L by del Pj. So, you can see the first term of the Lagrangian, only the term Pj when I equals to j will contribute, and that simply gives minus of 1 plus ln Pj, and the second term would give minus of minus lambda into 1, which is just minus lambda, and the final term would give minus beta into epsilon j, because only I equal to j term will contribute there, and epsilon is anyway a constant, the last term is 0, the derivative of last term with respect to Pj is 0. So, you can rearrange everything and obtain the value of Pj now. So, there is a 0 here. So, what you will do is you can write down logarithm of P of j as minus 1 minus lambda minus beta times E of j, and this will simply give you P of j as e raised to minus 1 minus lambda into e raised to minus beta of j. Now, look at the right hand side. This time the probability of the jth phase is dependent on j. Okay. Now, you can see it depends on j, because there is a term E j, which is in some sense the value of the phase j. So, this is called as non-uniform PDF. So, hence we will say that Pj turns out to be non-uniform. So, with the extra constraint that we had taken, our PDF has now become non-uniform, and this is actually a Boltzmann PDF, Maxwell-Boltzmann PDF, we shall see. So, our Pj is not yet normalized as can be seen. So, we will simply normalize Pj. So, normalize P of j, and to normalize this P of j I need to find a normalization constant, which is nothing but summation over all j's P of j. So, this will go from 1 to n, 1 to t, and because the value of P of j is given here, it simply becomes, if I sum it t times, this will simply be e raised to minus 1 minus lambda into summation on j P of j. So, with this normalization constant, our final normalized PDF becomes the unnormalized PDF, which is simply e raised to minus 1 minus lambda into e raised to minus beta times epsilon j divided by the norm that we have just obtained. So, we plug it here and it simply becomes right. So, I have just made a small typo here, thank you. So, this becomes e to the power minus beta e j, of course, and then you can write down the final answer as your normalized PDF, which is e to the power minus beta e j over summation j going from 1 to t e raised to minus beta e j. and this is nothing but your if you say that beta is 1 over kT and this where Ej's were nothing but the energy levels of jth state, then this is nothing but Maxwell Boltzmann distribution, where our normalization constant, okay, is also known as a partition function. So, in some sense this is like a partition function for your problem, which depends on beta. Okay. It does not depend on energy levels per se, because they are summed over all the levels. So, that is gone, but it is a parameter here is beta. So, this is the reason why we see Maxwell Boltzmann distribution everywhere around us if your system has constraints more than just the conservation of probabilities. So, if you set the average value of energy to some constant, then the distribution will come out to be Maxwell Boltzmann, and the consequence this is the consequence of the entropy maximization that you see Maxwell Boltzmann distribution profound in nature. So, this is one example that we have discussed, and I am going to give you one more example, a worked example, where the degrees of freedom are not discrete, they are continuous. Okay. So, what we saw, I am just going to summarize it. So, what we saw so far is basically two different types of PDF for the discrete case. One type of PDF was simply P of j as 1 upon T, I call it as a uniform PDF, probability density functions, and this comes if there are the only constraint is summation of probabilities which are conserved, or the probabilities are all they add up to 1. And the other case that we have seen is basically P of j, which becomes non-uniform. So, I have e raised to minus beta j over sum over, so I get a non-uniform PDF if I have an extra constraint. So, above the well behavedness of the probability, I have two constraints here. One that the probability is well behaved, the other is the probability the average value of the outcomes is fixed. Okay. So, I have two constraints here. And I have only one constraint here. Okay. And these constraints basically manifest in the type of PDFs that we obtain. Okay. So, that is the end of discrete probabilities. We will now move on to the case of continuous probability distributions. Okay. So, I am going to talk about the case of continuous probabilities. So, I am going to call this as not as a PDF, but actually just probabilities here, because they are discrete probabilities. And similarly here, to sort of be more accurate, I will call it as a probability. Okay. So, let us look at the case of one dimensional gas. Ideal gas. Okay. So, let us say that the ideal gas is some temperature T. Now, I know by equipartition theorem that per degree of freedom the energy contribution to an ideal gas is half k of t, half k t. Okay. So, so I can take the velocities for the case of an ideal gas to be just along the line x axis. So, this is the v axis, v is the velocity. Okay. So, I have some distribution of v and I know that the distribution is Gaussian or Maxwell-Boltzmann like, and I know the answer to be so we'll derive this distribution, and so what we really know here in this case is that my kinetic energy, average kinetic energy per degree of freedom is basically half k T by equipartition theorem. Okay. And I want to know what is my PDF. Let us say it is unknown, although we know from standard literature that the PDF is supposed to be Maxwell-Boltzmann like, but there is no formal proof presented to you so far. So, the task of this section is to show that the only PDF that is satisfied by the particles here is a Maxwell-Boltzmann PDF or a Gaussian PDF. Okay. So, we will prove that. Now, what are the ingredients needed for this proof? Well, first is definitely I need to know the function of the function that I am going to optimize or maximize, and that function is basically my entropy. Which is basically my entropy. And just as in the case of a discrete case, I will take my entropies to be instead of taking a summation, I will take it as a negative integral of p of p ln p of p dv. Okay. And the limits here are going from minus infinity to plus infinity. Okay. Now, if you are bothered by the fact that this p of p is dimensional and I have taken a logarithm of it, where it is not dimensional because I have divided by a p of scale of PDF which takes care of non-dimensionalization. Okay. So, these PDFs are all non-dimensional and consequently this velocity scale is also non-dimensional. So, all this non-dimensionalization leads to a constant of entropy here that I have taken to be conveniently 0, because at the end of the day I do not require exact values of entropy, I require a shift or the change in entropy. So, when you take for any practical purpose a delta S, the you can simply change this factor simply goes to 0 because it is just a constant. Okay. So, I am not writing it, but I am aware that this P of V is non-dimensional. Okay. So, now this is my entropy or the function that I am going to maximize. The second ingredient that I must observe or I must take into consideration is the fact that my PDFs that I am chasing are normalized. Okay. So, P of V is normalized, a very important ingredient. So, which means my constraint G is basically integral V going from minus infinity to plus infinity P of V dV minus 1, which is equal to 0. Okay. My PDF is normalized, that is my constraint. My third ingredient is one more constraint. I know from equipartition, just now we discussed I know that half mv squares average is just half kT. So, this basically gives me my constraint H. I am just going to write down my constraint H as simply integration V minus infinity to plus infinity the average value of half mv square, which is nothing but half mv square measured in this distribution minus half kT is 0. Okay. So, average value of any function of V is nothing but the, like we said, this is nothing but this this quantity, this integral is nothing but average value of half mv square. Okay. So, that is what I have written here. Right. So, now I have the function that I want to maximize. I have my two constraints G and H under which I am going to maximize my function S. So, I will use the concept of Lagrange multipliers and that is straightforward. It is just the same Lagrange multiplier business that we have done in the context of discrete probability, and it is very interesting. At the end of this optimization, you will see a natural emergence of Maxwell-Boltzmann distribution. So, let us do that and sort of firmly establish in our heads why nature, why mother nature always prefers a Gaussian distribution or a Maxwell-Boltzmann distribution for velocities for a system which is isolated, has been given enough time to evolve and reach thermal equilibrium at temperature T. Okay. That is the only reason for this observation is that a Gaussian distribution is the distribution of maximum entropy. So, let us do that. So, the same principle, maximization principle, leads us to the following equation. Let us write down the following equation. I will write down our Lagrangian as function f, this f is the entropy, minus lambda times g, where lambda is the Lagrange multiplier corresponding to the constraint g, another Lagrange multiplier which is beta corresponding to the second constraint h. Let us write down what are these quantities. So, my function f is nothing but the entropy, which is minus of integral v going from minus infinity to infinity p of v ln p of v dv, okay, minus lambda times g, which is nothing but use the space wisely, Okay. And now you simply take derivatives and say that this Lagrangian is maximized by some PDF which is P. I call it as yeah. So, this is the P that maximizes it, and so I have to set this to 0, okay. And if you take the derivative, this simply becomes, I am going to write down the entire thing under the integral. So, from the first term I get 1 plus ln P of v, okay. So, I am going to take derivative with respect to P of v, fine. And from the second term I get lambda times one, and from the third term I will get beta times mv square by 2, that is it, and this is an integral on v which is 0. I have already written 0, so it is not required. Now you can actually write down a 0 on the right hand side to sort of yeah, and we shall remove a 0 from here. Okay. Now you can see that the integral is 0 for all values of the integrand. For any arbitrary integrand. Okay, we are not specified that P of v has to be a certain type, only then this is 0. Okay. So, I can say that for this entire integral to be 0, my integrand has to be 0. Okay. So, which means I will write down my integrand as 1 plus ln P of v plus lambda plus beta mv square by 2 as 0. Okay. And so, you can simply write down P of v as e raised to minus 1 minus lambda into minus beta mv square by 2. And so, now you can see that this is also a non-uniform PDF. Okay. So, let us normalize it. So, I am going to find a normalization constant. Okay. This is nothing but integral minus infinity to plus infinity P of v dv, and that will come out to be e raised to minus 1 minus lambda. Integral of a Gaussian is the square root of pi by a. Pi by a itself is beta m into 2 pi. Okay. Fine. So, then our normalized PDF, I will call it as a velocity distribution, becomes P of v as simply the PDF that we have written divided by the normalization constant. It is e raised to minus beta mv square upon 2 into square root of m upon 2 pi k KBT. So, this is basically the Gaussian or Maxwell-Boltzmann distribution. Okay. So, this is the Maxwell-Boltzmann distribution of velocities. We can also obtain Maxwell-Boltzmann distribution of speeds by simply writing the distribution in terms of molecular speed, not velocities. So, the fact here is the reason why we get a normal distribution or a Maxwell-Boltzmann distribution is the fact that this is the distribution of maximum entropy. So, this basically is a formal proof of why you see certain types of distribution more often than the others, and especially for equilibrium systems this is the preferred distribution, or in fact this is the only distribution, not a preferred distribution. So, we end the lecture here, and this basically completes the chapter 1 of our syllabus. In the next chapter we will talk about basic postulates of statistical mechanics, and in this context we will discuss various important ensembles and discuss examples, physical examples where the ensembles are relevant. Okay. So, we end it here.